Hi, I'm Ashna, and I will be presenting our work titled Leveraging Data Recasting to Enhance Tabular Reasoning. Tabular inference is a problem very similar to standard NLI, where instead of unstructured text, we consider our premise to be tables, which are a semi-structured data form. So, given a table and a hypothesis, the task is to determine whether the hypothesis is entailed, contradicted, or neutral. So tabular NLI requires a lot of supervision data to learn complex reasoning on semi-structured data. This is because in semi-structured data forms such as tables, we do not capture information only through text, but also through positioning and structures. Two primary ways of generating supervision data is either through human annotation, which creates extremely fluent, linguistically versatile data, but it is very hard, time-taking, expensive, and it also introduces some annotation artifacts and bias. On the other hand, we have synthetic data generation methods, which are very easily scalable, very cheap, and time efficient, but they lack the kind of creativity and diversity that comes with human annotation. So we ask ourselves this question: can we generate data that is as scalable as synthetic data and yet contains the human like fluency that we get from human annotations? In this research, we answer this question through the lens of data recasting. What we mean by recasting is that we take examples from non-NLI datasets and we somehow perturb them, transform them, augment them to fit into the definition of an NLI task. So in this example, I've taken some data point from a table to text generation dataset, and I've transformed it to create entailments and contradictions, basically um, transform it in a way that it fits into the definition of NLI. Recasting comes with several benefits. First and foremost being that source datasets are human annotated, which means that I can retain the diversity and creativity that comes with human annotation. Secondly, since the recasting process is automatic, it's very fast and it's very cheap as compared to human annotation. It also allows us to create data in a large volume, and it also allows us to control distribution and annotation biases. In this paper, we propose a semi-automatic framework for recasting tabular data. We end up recasting 5 source datasets from table to text generation, table question answering, and table semantic parsing. Then we utilize this data as an evaluation benchmark, as data for augmentation to enhance performance on TabFact, which is a benchmark NLI dataset. And we also train models on our dataset and test them in a zero-shot setting on TabFact. Before we move on to the framework, I would like to talk about some prerequisites that we need. One is, of course, a table. We also need an annotated description, which is true on basis of the table, something to start with. And we also need alignments between the statement and the table, which would be through relevant cell information. For creating entailments, first of all, we draw these alignments between an annotation and the table. Once I have the highlighted cells, what I need to do for making entailments is replace all highlighted cells with potential candidates from the same column. While doing this, I also have to make sure that if 2 or more entities are coming from the same row, for example, party A and 120 here, they are simultaneously replaced with something else from a different row. We also paraphrase sentences to add lexical diversity to our dataset. Creating contradictions is slightly easier because the constraints are more lax. I can try to contradict any one part of the sentence, which would make the entire sentence false. While doing this, there is also chance that we accidentally make new entailments. To avoid this, we don't just see that we are replacing something with a different row, but we also check the value to ensure that the truth value of the sentence is maintained. Till now, we discussed perturbing the hypothesis, but it is also possible to perturb the premise, which is the tables. So we take highlighted cells, swap them with potential candidates to get new tables, which we call counterfactual tables. We also replace the swapped value in the original annotation, which gives us new entailments, and then we can go on applying the framework as we have done before. Few challenges that we faced while working with this framework. First of all, alignments between sentences and tables aren't always explicit. Sometimes numbers are expressed as words, full names are boiled down to surnames or first names, similar issue with locations, and same issue with dates. Another challenge that we faced is that our framework assumes that tables are vertically aligned, which means that the headers are in the top row and each column contains data of the same type. But in several source datasets, we find that tables are horizontally aligned. In such cases, we apply heuristics to identify horizontal tables and we flip them by 90 degrees so that we get vertical tables, and then we apply the framework to them. Another challenge is that some entities are completely irreplaceable. For example, entities coming in total rows or aggregate rows or mean rows, they cannot be replaced by anything else if we want to maintain the truth value of the statement. This is something that we should also observe while creating counterfactual tables. We should not swap entities with irreplaceable ones. We recast 5 human annotated non-analyzed datasets, 2 from question answering, 2 from semantic parsing, and 1 from table to text generation. While recasting table to text generation datasets is fairly straightforward, for recasting QA datasets, we have 2 forms. We either have short form question answering, in which case we combine the question and answer using a sequence-to-sequence model into a statement that becomes our base entailment. Or we have long form question answering, in which we have a sentence that's the answer, which in itself is an entailment, so we go on from there. For semantic parsing datasets, we have an interesting situation. We have a question and an SQL query. So first we can execute the SQL query. We get a short form answer, which we can combine with the question using a sequence-to-sequence model as described before, and create a base entailment. And then we can create contradictions from there. But since we have an SQL query with us, we can actually replace values in the SQL query and the question parallelly. And then we have a new SQL query that we can execute, get answers for, which we can combine with the new questions and get more statements. So this is a nice foolproof way of creating new entailments because we actually get to execute the query to find the answer. Squall is a semantic parsing dataset that comes with a lot of metadata. It gives us alignments between the question and the SQL statement, which means that we can boil down questions and SQL statements to skeletons, as shown in the example here. When we can do this, we can apply these skeletons to not just the table that they are derived from, but to any other table that satisfies the conditions mentioned in the skeleton. We end up with 5 resultant datasets, but we combine both the QA datasets together to get volume. The downstream task that we choose for testing our model and our data on is TabFact, which is a large-scale benchmark table analyte dataset. We answer 3 research questions. The first thing that we think about is, can our data be used as a challenging test set for existing NLI models? So we take the Tapas TNLI model trained on TabFact and test it on our created recasted datasets. And as shown here, our data proves to be a challenging evaluation benchmark. The second question we answer is, can our recasted data be used as augmented data for existing NLI tasks? This table shows some baseline values, and we build on top of tapas plus table analyze, which is a pre-training model pre-trained on counterfactual and synthetic data. We take this as our base model and we use our data for pre-training as well. With our data, we are able to observe an improvement of 1.1% from the baseline that we start with, which is over 17% from the first baseline that's given in the TAPFAC paper. The third question that we try to answer is how well models trained on recasted data can perform in a zero-shot setting. As shown in the results here, our models give greater than 80% accuracy on TAPFAC simple test sets in a zero-shot setting. We also outperform existing models in this case. I would also like to discuss some limitations that we observe. First of all, source dataset type does affect the quality of the data because, say, generated text is likely to be descriptive as compared to extremely complex. Similarly, since no two datasets can have the exact same distribution of categories and themes, we do introduce an unintended domain transfer task when we use recasted data for pre-training. Last but not the least, a lot of data ends up using common sense and general knowledge, which is hard to recast. To summarize, in this research, we propose a semi-automatic framework for tabular data recasting. We use this framework to generate 5 different data sets, and then we show that we can use this data effectively as an evaluation benchmark for augmentation and also in the zero-shot setting. Thank you.